Over the last few videos, we saw spring mass systems. So first we saw spring mass systems on a horizontal table, then we saw spring mass systems hung from the ceiling vertically. So we have seen vertical spring mass system, horizontal spring mass system. Now let us look at a spring mass system along an inclined plane. So the question is, a block weighing 14 Newton. So this is the weight is given. So weight is nothing but mass times the acceleration due to gravity. So a block weighing 14 Newtons, which can slide without friction. So even in the horizontal case, we considered that there is no friction, and in the vertical case there is no question of friction. So which can slide without friction on an incline at an angle of theta equal to 40 degrees. This is the inclination angle. So this block is connected to the top of the incline by a massless spring of unstretched length. How much is the unstretched length? Unstretched length of 0.45 meters and spring constant (120 Newton per meter). So the question is, there are two parts. How far from the top of the incline is the block's equilibrium point? So we need to find out the equilibrium. The next question is, if the block is pulled slightly down the incline, pulled slightly down along the incline and then released, what is the period of the resulting oscillations? So this is the question. So let us now start solving this question. Let us look at the first part. So in the first part, we need to find out the equilibrium position. So let us redraw. sorry, I'm drawing it for the first time actually. So the diagram is as follows. This is the inclined plane. This is theta equal to 40 degrees of the incline. Then this is the wall, and here we have the spring, and then the block is on the inclined plane. So if I just draw the spring, so this is the natural length of the spring when there is no block. Now when I will attach the block to the spring will extend due to the weight of the block. So its equilibrium length will change. So if this is L, this is the natural length. Now when I attach the block, so when I'm attaching the block, the spring will extend and the equilibrium position will change. So this was the original natural length of the spring. So this is our natural length L. This is the extension coming in due to the block being attached. So the weight of the block will pull the spring downwards or extend the spring, and we will have a new equilibrium position. So this is still the equilibrium position. We are not displacing the block. So let us call this, let us draw our axes first. So since all our motion is along this incline, it makes sense to call this the x-axis. We will have our x-axis along the incline. So this is, let's say, some distance x0, extension for the equilibrium. So in part A, we know that the block is in equilibrium. So what are the forces acting on the block? If we draw its free body diagram, then the forces acting on the block are the restoring force, and the weight, the gravitational force mg. Now we can resolve the components. So this is the inclined plane direction along which the force is, or the restoring force is being applied by the spring on the block, and this angle we know is theta. So this angle right here would be 90 minus theta. This angle also here would be 90 degrees minus theta. So if we write down the components along the incline, so along incline, so remember this is in equilibrium. So equilibrium means that net force is 0 and everything is stationary. So this is equilibrium. So if we write down the components of the forces along the incline, then we will see that in equilibrium the forces are Fr, and due to this weight we will have a component. This would be mg cosine of 90 degrees minus theta is equal to 0. So net force along the incline is 0, and we have taken this downward direction as the positive direction. So restoring force is being applied opposite to the force of the gravity along the incline. So this gives us since cos 90 degrees minus theta is sine theta, and by Hooke's law the restoring force is k times x naught being the extension. So this is coming from Hooke's law. Which says that the restoring force is negative kx. Negative sign signifies that the direction of the restoring force is opposite to the direction of the displacement. So our displacement is downwards, so the restoring force is being applied upwards. So this negative sign takes care of that. Otherwise the magnitude is k times x, x being the displacement. So this gives us that x naught is equal to mg sine theta over k. So this is what we were supposed to find out. We were supposed to find out the extension after equilibrium. So it says how far from the top of the incline is the block's equilibrium point. So this is the extension after the natural length. So total length of the spring in equilibrium, this is going to be how far from the top. So this is nothing but L plus x naught, because in equilibrium the block is attached, the spring gets extended by x naught, and its natural length originally was L. So how far from the top of the incline is the block's equilibrium point? So the block is essentially at this location, which is L plus x naught downwards. So this is essentially block's position along the incline. From the top. This was what we were supposed to find. So this is this value, and then plugging in the numbers, we have L being given as 0.45 meters plus x naught. X naught is mg sine theta by k. Mg we are given as 14 Newton. Sine theta is sine of 40 degrees. And k is nothing but 120 Newton per meter. So if we plug these values in a calculator, we get roughly 0.0525 meters. This solves the first part, in which we were supposed to find out the block's equilibrium position and the distance from the top of the incline to the block's equilibrium position. The next part is to find out the time period of oscillations if the block is displaced and released. So let us draw the diagram. Let us once again draw the diagram. This is part B. So this is the spring, and then we want to displace this block by a certain distance, this distance being x. We want to displace the block, and this is the equilibrium length, so this is L plus x naught, this distance right here, and from here we want to displace the block to a new location. Let me redraw it. We want to displace the block to a new location over here, and this is x distance or displacement. In this situation, we need to find out the time period. Now, from Hooke's law, we know that the restoring force is minus of k times the displacement here being x. So the net force on the block is this restoring force, because in the equilibrium position the force due to gravity and then the force due to extension x naught in the spring gets balanced out because it's the new equilibrium position. Once the equilibrium position is attained, after that we will extend the block furthermore by x distance, and that will lead to a net restoring force on the block, which will lead to simple harmonic oscillation. So this force is nothing but mass times acceleration. This is nothing but this, and this gives us this again is nothing but the equation for SHM. Standard equation for SHM, with omega being square root k by m. This term right here, k by m, is omega squared. So our time period is 2 pi by omega, which is 2 pi root m by k. So this is the time period, and if we plug in the values of m and k, so we will find out the value of the time period. T is 2 pi square root, m is nothing but 14 newtons, the weight, divided by g, or g is 9.8 meters per second squared, divided by k is 120 Newton per meter. So putting it in a calculator gives us 0.686 seconds. So this is the time period. Notice that this time period for oscillation of a spring mass system is universal. Universal in the sense whether we have a horizontal spring mass system, vertical spring mass system, or spring mass systems on an incline, this time period remains unchanged. So this is kind of some, you can say, some sort of universal feature this time period has. So it's kind of universal in the sense that the time period is same in all three cases that we saw. So whether you have a horizontal spring mass system or a vertical spring mass system or an inclined spring mass system, the time period is same for all these three cases. So what changes in all these three cases? Well, the equilibrium position changes in all the three cases. In the horizontal case, the equilibrium position is the same as the natural length of the spring. In the vertical situation, we saw it one of the previous videos. I can show it over here if I scroll it upwards. So we saw that the equilibrium position was shifted in the vertical case by this much amount, by mg by k. So by mg by k in the vertical spring mass system. In the inclined spring mass system, the extension, the new equilibrium position is mg by k times sine theta. So only the equilibrium position changes, the time period is same in all the three cases. So if I write down, if I summarize this, we have horizontal case, horizontal spring mass system. So equilibrium position is same as natural length of spring. In the vertical case, the equilibrium position is shifted by how much? Shifted by mg by k. So it is natural length plus mg by k. That is the total length of the spring in the equilibrium for vertical case. In the inclined case, this shift is determined by the angle of inclination. So equilibrium position is shifted by a distance mg by k times sine theta along the incline. But in all the three cases, our t remains the same. So this is something important. Please keep this in mind. Whether you have vertically hanging springs, horizontally kept springs, or springs down an incline, the time period remains the same.